enhance the technical competence of the students,
waiting sir, அதுக்குள்ள 8 பேர்
learning
வந்திருக்காங்க.
and lab integrated courses. The department
கேக்குது அது எங்க இருந்து
ஓபன் ஆயிடுச்சு சார். ஆனா பிக்சர் வரல, சவுண்ட் தான் வருது.
இந்த கோடு கோடா வருது. யூடியூப்லயும் இந்த குரூப்ல பேசுறதெல்லாம் யூடியூப்ல கேக்குது ஹசன். ஓகே ஓகே இப்போ பேண்டா ஸ்கிரீன் பண்ணாதீங்க. ஏற்கனவே 5-6 பேர் வேண்டாம் அவங்க ஏற்கனவே நிறைய பேர் வெயிட்டிங்ல இருக்காங்க போல.
8 பேர் இருக்காங்க மேம்.
அதனால இப்ப அதுல வந்து இப்படியே நம்ம சும்மா என்னென்ன வீடியோ கிரசன் சாட் ஒண்ணு போடுறீங்க டிபார்ட்மெண்ட்.
A man is not poor without a rupee, but a man is poor without dream and ambition. Learn, innovate and empower.
The Electronics and Communication Department of B.S. Abdul Rahman Present Institute of Science and Technology is established in the year 1994, celebrating its 25 years of excellence, accredited by NBA, aspires to be a leader in education, training and research in multidisciplinary areas of importance and to play a vital role in the socio-economic progress of the country.
The institution is renowned for its technical competence, intellectual character, commitment to excellence, community focus. What creates an indispensable future? Charging a neuron to wave at the world
with the brains as a transmitter, enchanting the engineer look.
Electronics and Communication Department is known for its excellent lab facilities, 14 in number with highly motivated faculty. In the focus to develop the interest of the students, the department has inaugurated clubs like Hobby Electronics Club, V-Quiz, a quiz club, Service to Society Club and EC Got Talent Club.
The department has signed MOU with many prominent companies such as Jasmine Infotech, Nokia and National Instruments. The students are provided with internships and the best performers are placed the same.
Crescent launches its satellite and the Department of ECE is very proud to contribute 13 students along with the faculty. Designed, developed and test launched on 24th February 2019.
The team is led by Dr. S. Kaja Moidin and now the team is involved in design and development of suborbital satellites.
It will be always remembered people who launched the first Crescent satellite.
The department offers value-added programs like CLAD, AutoSAR and Frag Robotics. To enhance the technical competence of the students, the department offers project-based learning and lab-integrated courses. The department provides opportunities like transferring credits through online courses via NPTEL.
The department, along with the placement cell, provides the soft skills and gives extra focus on training the students for the placement.
The department also has an excellent rapport with its alumni.
The department also supports and motivates in developing the extracurricular activities of the students.
The department is a consecutive winner of the IET Student Chapter for the past 2 years. We encode the heart with solutions and decode it. Yes, we are EC engineer, and ECE would be the right choice to head in Crescent institutions. Come, learn, and develop as a leader.
If you want to shine like a sun, first burn like a sun. Myself Samilla from Electronics Communication and Department. The selection process includes technical writing, programming, and one-on-one interview. After the selection, 20 members got selected and we formed Team Crescent.
To get succeed in your mission, you must have single-minded devotion in your life. I'm Yashri from BS Abdul Rahman, Crescent Institute of Science and Technology, pursuing my third year EC. I'm very happy to be a part of Team Crescent. This project helped me to learn all the new technologies like Raspberry Pi, Arduino, etc. We have successfully test launched our first Crescent prototype model in the month of February 2019, before which we had 1 month of training. Apart from our scope of interest, we had huge support from our Vice Chancellor, Registrar, Dean, HOD and other faculties of EC department.
We have to dream first to make them happen. This is Sheikh Mohammad Azruddin from the Electronics and Communication Engineering Department. I am very proud to be in the team of Crescent. We have given a very great opportunity of visiting Malaysia as a part of international outreach for our project Crescent. We visited UITM, which is located at Shah Alam in Malaysia. We met many professors as well as the junior and senior satellite making teams over there. They also took us around the UITM University and they showed us many futuristic labs like the Dream Lab, Antenna Research Lab, the Satellite Research Lab, which gave us a great knowledge and a great exposure on the present trend in the industries. We also gave a presentation in UITM Malaysia regarding the high altitude ballooning which we did in the month of February. We had a knowledge sharing session with the UITM satellite team where we exchanged ideas, took suggestions for our upcoming future launch. We are provided with a satellite research lab by the Electronics and Communication Engineering Department as our workspace and to conduct research studies.
If you want to shine like a sun, first burn like a sun. Myself Samilla from Electronics Communication and Department. The selection process includes technical writing, programming, and one-on-one interview. After the selection, 20 members got selected and we formed Team Crescent Sat.
To get succeed in your mission, you must have single-minded devotion in your life. I'm Yashri from BS Abdul Rahman, Crescent Institute of Science and Technology, pursuing my third year EC. I'm very happy to be a part of Team Crescent Sat. This project helped me to learn all the new technologies like Raspberry Pi, Arduino, etc. We have successfully test launched our first Crescent Sat prototype model in the month of February 2019, before which we had 1 month of training. Apart from our scope of interest, we had huge support from our Vice Chancellor, Registrar, Dean, HOD and other faculties of EC department.
We have to dream first to make them happen. This is Sheikh Mohammad Azruddin from the Electronics and Communication Engineering Department. I'm very proud to be in the team of Crescent Sat. We have given a very great opportunity of visiting Malaysia as a part of international outreach for our project Crescent Sat. We visited UITM, which is located at Shah Alam in Malaysia. We met many professors as well as the junior and senior satellite making teams over there. They also took us around the UITM University and they showed us many futuristic labs like the Dream Lab, Antenna Research Lab, the Satellite Research Lab, which gave us a great knowledge and a great exposure on the present trend in the industries. We also gave a presentation in UITM Malaysia regarding the high altitude ballooning which we did in the month of February. We had a knowledge sharing session with the UITM satellite team where we exchanged ideas, took suggestions for our upcoming future launch. We are provided with a satellite research lab by the Electronics and Communication Engineering Department as our workspace and to conduct research studies.
Dr. C. Tarini, HOD ECE, to grace the session with the welcome address. Ma'am.
Thank you, Dr. Vijayalakshmi ma'am. Hi all, everybody out there. Good evening and good morning to Dr. Professor Daniel Leon-Salas, Associate Professor from Purdue University. Sir, I welcome you for this webinar on optical communication through solar cells. And thank you so much for accepting the invitation. And we all definitely know that you are going to share us a lot of information through this webinar. And before we proceed with our webinar, I would like to say a few words about Dr. Leon-Salas. His research interest is in solar optical communication, data compression algorithms, and he has completed many funded projects, both from public and private domains. And he has very good publications, good number of publications with him. And once again, I thank you so much for having accepted our invitation. And even though it is very early for him, he is now here online to share his expertise with us. And I would also like to say a few words about our department at present, Institute of Science and Technology. And this department was established in the year 1994. And since then, we have grown and we have very good infrastructure in almost signal processing, embedded system, VLSI, and communication domain. And I'm proud to say that one of our research scholars was with Dr. Leon-Salas for the past 1 year and was pursuing her research over there in his lab. And right now she has come back to our institute to continue her research. And I would like to mention a few words about the industry rapports which we have. We have an MOU with National Instruments. We have an MOU with Jasmine Infotech, which is a core signal processing company. And I'm proud to say that we are one of the very few institutions, departments, which have an MOU with the Jasmine Infotech. And we offer value-added courses on automotive embedded systems, and then CLAD certification, CLT certification. And we have our alumnus throughout the world doing great in holding eminent positions. And recently, during this COVID pandemic situation, one of our alumnus has come up with Zaki Robo, and now this robo is used in almost all the hospitals like Stanley Medical College, Tanjavur Medical College, for giving COVID patients food as well as medicine. So with these few words about our department, I would like to ask Dr. Vijayalakshmi to introduce our professor, Dr. Leon-Salas, to the audience. Thank you, ma'am. Thank you, one and all. And now to Dr. Vijayalakshmi.
Thank you, ma'am. Thank you. Good evening, everyone and all present here. Through this webinar, we got the opportunity to meet once again. I am Vijayalakshmi, Professor, ECE. Thank you for the opportunity. It gives immense pleasure to introduce today's resource person, Dr. Walter Daniel Leon-Salas. Dr. Walter Daniel Leon-Salas, serving as Associate Professor, Purdue University, USA, from 2016 to current date. Prior to this, Professor served at various institutions like University of Missouri, Kansas City, University of Nebraska, Lincoln, NE. Also, he has industrial exposure by working Telefoncia, Dell at Peru, and at Equipa and Lima at Peru. Professor research interest includes CMOS image sensors, data compression, RFID based sensors, compressive sensing, energy harvesting, optical communications, flexible electronics, and programmable hardware wireless sensors. To add his credits, Professor has many patents, namely system and method for generating pseudo-noise sequences, apparatus and system for low voltage, direct current, and industrial power recharging of hybrid, high occupancy, capacity on-road transportation vehicles. Likewise, so many patents, okay, sir is holding. Professor has executed 15 successful projects funded by government and non-government funding agencies. To name a few: Center for Technology Development, National Science Foundation, Toyota Motors, QF Power, CERC, etc. are the project done by the professor. Professor has published enormous papers in the reputed journals, which includes IEEE Sensor Journals, BMC Neuroscience, IEEE Transactions and Circuits and Systems, etc. And Sir is acting as a review member in IEEE Transactions also, and his new ideas were presented in 41 different international conferences and journal publications. Adding feather to his credits, Professor has won the Outstanding Faculty in Discovery Award at Purdue University in November 2014, National Science Foundation Career Award, Leadership Excellence Achievement Program Award from the Missouri Society of Professional Engineers, Outstanding Doctoral Dissertation Award from University of Nebraska-Lincoln. For the purpose of research, Professor visited almost all the parts of Asia, Japan, India, and more. Now, I request Dr. Walter Daniel Leon-Salas to continue this webinar session for the knowledge transformation. Professor, could you?
Thank you very much for this kind introduction, and I'm very glad. I'm very pleased to be with you today, although remote through the internet, to have this webinar. I remember my stay at Crescent, Chennai. I have good memories. It was the last trip I had this year. The first and the last trip I had this year was to Chennai, to Crescent, and then the quarantines came. Right, so now we're all trapped. We're still here trying also to reopen Purdue, but it's happening very slowly. So one in a lifetime. I think this pandemic is affecting all of us. And what a great idea to have a webinar. I think looking forward, I think this is going to be the way we have to conduct meetings or conferences for a while, online, to avoid direct social contact. So thank you also for your time. I realize it's very late Friday night over there in Chennai. Here is early morning, 9 a.m. On a Friday, so I'm up and fresh, and I realize it's the end of your day for you. So thank you for taking the time at this time of the day or the evening to listen to me. Okay, I hope that it's going to be informative. I'm going to try to be brief. I know your time is very important, and it is late Friday evening over there. So what I'm going to do now, I'm going to switch to my PowerPoint presentation, and I'm going to present for about 40-45 minutes, and then we'll have questions. And I think you can write your questions, I think, on the chat box, and then I guess we're going to wait until the end for your questions, and I can answer your questions. All right, so let me share my screen. All right, so this is the title of my presentation. Optical communication with solar cells. Right, so that's a interesting topic for us. We've been working with solar cells for a while, and recently, in the last 3 years, we started working with using solar cells to transmit and receive information. So here's the title. I would also like to say that we come to this topic, we're approaching this topic from the circuits and systems perspective. Okay, so in our lab, we work with circuits, that's our expertise. We also do data processing, signal processing, data compression, and things like that. But our core expertise is circuits and hardware. So we come from that perspective. All right, so this topic of optical communication is a very large field, and different people, work from different angles. But our angle is the circuits. So it's going to have that flavor, all right, from the circuits perspective. All right, so let me start with introducing the concept of luminescence. Okay, so luminescence is a phenomenon that of emission of light from a material that is due to some stimulation, but it's not due to the increase in temperature. Right? Like, for instance, incandescent bulbs, they emit light because they are very hot. Right? That wouldn't be luminescence. Okay, luminescence is when a cold material is excited either through electricity, through photons, or chemical excitation, and that material emits light. We call that luminescence. For instance, there are many examples. Bioluminescence, right? So when the excitation is biological or chemical, and you have all these animals, especially in the sea, or fireflies even, right? They emit light, especially at night, and that's called bioluminescence. We also have photoluminescence, a material that if you illuminate it, for instance, with UV light, they glow. We have quantum dots, for instance, and they have these properties. So photoluminescence, the excitation is light, is photons. And this material emits photons of a different color, different wavelength. Or LEDs, for instance, LEDs also have luminescence. We call it electroluminescence because the excitation is electricity, charges. And this material, when it's stimulated with electricity, emits light. So electroluminescence. So semiconductors are special type of materials. They also, of course, LEDs are semiconductors. They have very strong luminescence. They've been engineered to have that. But semiconductors, just like silicon, for instance, yes, the silicon material also have this property. You can illuminate silicon, for instance, with blue or UV light, and it's going to emit back an infrared light. Okay, so this property of silicon is actually used to study solar cells. Okay, to find defects or even measure properties such as the resistance of the mobility of the material. It's very weak for silicon because it's an indirect bandgap semiconductor. Photoluminescence is very weak. It can be detected, but it's very weak. You will need a very special camera with long integration times. You have to wait a few seconds, if not a minute, to be able to detect this very weak light coming from silicon. But there are other kind of semiconductor materials, gallium arsenide, GaAs, for instance, here having my slide. Let me turn on my pointer. Let's see here. So gallium arsenide is another semiconductor that is direct bandgap. Right? So it's much more efficient than silicon in terms of emitting light, in terms of luminescence. So we can illuminate a piece of gallium arsenide material with light, and it's going to emit infrared light in this range, in the 870 or so nanometers. All right, and it's going to be much more efficient than silicon. All right, so here I have a photograph of gallium arsenide solar cell. All right, so here I want to highlight this publication that appeared back in 2012 from Professor Jablonovich's group. They do work a lot with solar cells and gallium arsenide in particular. And in this paper, they show sometimes perhaps counterintuitive result. And they say that a good solar cell should be designed to emit light, to be a good LED, right? So that's counterintuitive, because you might think that a good solar cell is a solar cell that absorbs a lot of photons and doesn't emit photons back, because if it would emit a photon back, we'll be losing that photon. But no, Professor Jablonovich's group saying, no, is the other way around. It should absorb photons, of course, but it should be also able to emit them back as luminescence, okay? And a strong luminescence is a sign that a solar cell is very efficient, all right? So using this principle, they've been able to design and build the most efficient solar cells, single junction solar cells that are available in the market. They started a company called Alta Devices that makes solar cells based on gallium arsenide using this principle. And these solar cells are very, very efficient. They have 28.8% record efficiency for single junction solar cells. And one of the tricks they do is they place a mirror underneath the gallium arsenide material, and the mirror helps internal photons to reflect and do a second pass through the semiconductor material. So have more chances to recombine.
Sir, Professor, sir?
Yes?
Sir, sorry to interrupt, sir. Your slide is not completely visible. Yes, sir.
You see the whole thing now?
Yeah, now good to go, sir. You can
Good, all
continue.
right. Sorry for that. I didn't realize it was being chopped. All right, so we were able to buy some of these solar cells from Alta Devices. The bad news is Alta Devices now closed. They're out of business, and they had to furlough their employees. And so I hope they can find more investors to bring them back. They make some of the most efficient solar cells out there. In any case, when they were still in business, we were able to buy some of these solar cells. I'm going to show you an experiment that we did. Here you see this photograph that you see here is being taken with the camera that can see the infrared. Okay, so you can see it's all black and white. It's because it's being recorded or being captured with a camera that has a filter for the infrared. So here you see infrared light. Okay, and this is the solar cell. It has two wires, positive and negative. And here you see this white portion here. That's the infrared light that this solar cell is emitting. Right? So right now, in this experiment, it was very sunny outside, so it's a sunny day. It was very, very strong sun, and so the solar cell is absorbing all these photons from the sun, visible photons and invisible photons also. It's absorbing those photons, and internally, those photons are getting converted to a charge, to an electron, and those electrons, when they recombine, they emit infrared photons, and those infrared photons is what you see here, this white portion here. Okay, so that's that. Now I'm going to show you a video. So this is me. This is again the solar cell. You see this white portion is the infrared light being emitted. Again, because the solar cell is being stimulated by sunlight. Again, this is very strong light. This is a summer day outside. A very strong sunlight falling onto the solar cell. And the solar cell absorbing those visible photons from the sun and emitting back infrared photons. Now I'm here holding the terminals of the solar cell, and what I'm going to do, I'm going to short the terminals of the solar cell. Right now they are open. Okay, I'm going to short them, and we'll see what happens. I'm going to run this video. You see, when I short it, that solar cell goes dark, right? Open, short, open, short, open, short, right? So what happened here? So when I shorted these wires, the luminescence turned off, right? It went dark, right? Why is that? And we'll repeat this experiment. In this case, this is a parking lot. Okay. Again, it's a very sunny day, and here I have a camera. Again, this camera can see the infrared. Here I have the solar cell on a laptop, and instead of me doing the short with my hands, I'm going to put a transistor, a MOSFET, to do a short for me. And with a MOSFET, I can do it faster. Okay, with my hands, I can do maybe one short a second, but with a transistor, I can do much faster switching. All right, so let's see. I have a video here as well. Let me play it. And can you see here the solar cell blinking? All right, you can see it. You can see that blinking as well, right? So instead of me doing that short, it's a transistor MOSFET doing the short. So why does it happen? All right, so the reason for this is when the solar cell is in open circuit, you know, all these charges being generated inside a solar cell, these electron holes, they have nowhere to go because the solar cell is in open circuit. These terminals are not connected, so they cannot leave the solar cell. Okay, those electrons inside the solar cell, they cannot leave the solar cell. So the only thing they can do is recombine, meaning they lose the energy they have. They fall back into the valence band, and by doing that, they emit a photon, an infrared photon. That's what you see here. But when I close the circuit, now those electrons can come out of the solar cell. They can leave the solar cell, so they don't recombine inside the solar cell. They don't emit back an infrared photon, and that's the reason. Here, let me show you an experiment. This is going to be indoors. Again, the gallium arsenide solar cell. All right, and instead of having sunlight falling into the solar cell, I'm going to apply a voltage to it, one volt, about 1 volt. And then I'm going to, again, record what happens to the solar cell as I do this, right? I have to say this 1 volt is square wave, so it's going to be 1 volt and 0, 1 and 0, 1 and 0 at the speed of 5 hertz. So let's see what happens. As you can see, the solar cell emits light, and you can see the flashes, right? And it's quite strong. It's so strong that you can even see the reflection from the table and from the wall, right? And this is a distance of 5 feet, about, almost 2 meters. And we can try this again from a longer distance, from about 5 meters. And this across the room, you can still see it, very, very clearly, very strongly, the solar cell flashing, right? So with these two experiments, what I show you is that these gallium arsenide solar cells have these properties of electroluminescence, right? That's when I apply the voltage to the solar cell in these videos. And photoluminescence, that was the previous experiment, the previous slide. When sun is shining on the solar cell, and the solar cell is emitting back infrared. That is photoluminescence, and this is electroluminescence. Also, I show you in the previous slide that you can modulate luminescence. You can modulate photoluminescence by doing the short circuit, right? Open and short, open and short. You can modulate photoluminescence. And if you do electroluminescence, like in this experiment, you can apply a square wave and you can turn on and off at will by electroluminescence. All right. So we said, hey, I think we can use this. This is an interesting phenomenon. We can use this to our advantage, to something practical. If we can control the luminescence of a solar cell, both photoluminescence and electroluminescence, then perhaps we can transmit codes. We can transmit a message, we can transmit bits, and we can make it in something useful. All right, and when we were looking at this phenomenon, we realized it has many parallels with the RFID. In RFID, as you might know, you have a reader. Let me turn on my pointer again. You have a reader, and you have an antenna, and this antenna is transmitting a wave, an electromagnetic wave that is captured by another antenna, a coil antenna. And here we have a switch, and this switch is doing an open and short, and this antenna is reflecting and not reflecting, reflecting and not reflecting some of this electromagnetic wave back to the reader. That's how RFID works, right? And so it reflects or not by playing with this switch. So basically it's changing the impedance of the tag antenna, okay, from going from a short to an open, and that gets reflected back to the reader, and the reader can detect that. So we saw some similarities with what we're trying to do, because we also do an open and short when we do a photoluminescence. And so we said, we're going to call this OFID, and that would stand for optical frequency identification, just like RFID stands for radio frequency identification. We said, well, because of that similarity, let's call it OFID. Also, it's a name that people can remember. And OFID, what we have is a device here, and this will be the tag that has a solar cell, a gallium arsenide solar cell. And this solar cell is being illuminated by a reader. So here, this will be the reader, and the reader has an LED and some optics that can illuminate the solar cell on the tag. And here we have some circuits, right? So this luminescence modulator will be just a simple switch, a MOSFET, if you will. It's doing the open and short condition for this solar cell, and this solar cell is going to change its luminescence based on whether you have a short or an open circuit here. And therefore, luminescence, the infrared luminescence is going to go, some of it is going to be captured by the reader, again with some optics here. A photodiode can amplify that, we can recover that. At least in principle, we can recover those bits that were sent by the tag. Okay. So that will be communication in this direction from the tag to the reader. But the reader can also send information to the tag. You know, if you can modulate this light, okay, you can turn on and off this light from the reader. The solar cell, by virtue of its photoconversion property, it will convert that blinking light into a current that can then be converted to a voltage, and therefore we can receive information or data from the reader by the reader modulating the light that puts out. Right, so we can have also a communication in this direction from the reader to the tag. Okay, we'll call it the downlink from the reader to the tag, and from the tag to the reader using the photoluminescence, it will be the uplink. Okay. But of course, a solar cell is a solar cell. It's being designed to harvest energy, radiant energy, right? So we shouldn't forget that, right? So we will also like to have here a circuit. I'm calling it an energy harvester, but it's basically a circuit that's doing what a solar cell should be doing, right? Converting light into electricity, and then using that electricity to charge either a battery or a capacitor, right? That's the primary function and the intended use of a solar cell, right? To harvest energy and power something up. All right, so that will be the OFID concept, right? So the tag will have, you know, three functions. First, transmission of information using luminescence, reception of information using the photoconversion property of the solar cell, and also harvesting energy from the solar cell. All right, so the tag can be fully passive, right? So if we have the reader always illuminating the solar cell, therefore we can have a tag that's fully passive, meaning it doesn't have any batteries. You know, it wakes up the moment the reader illuminates the solar cell, it wakes up, it powers, it energizes itself, and it does something. Okay, so it can be fully passive. That's what I'm highlighting here. Now, in this case, the reader was active in the sense that it's actively illuminating the solar cell, but depending on the situation, we might have a different scenario where the reader is passive, so the reader does not illuminate the solar cell. Instead, the solar cell is illuminated by ambient light. In this case, sunlight, like I showed you in a previous experiment, sunlight will energize the solar cell and stimulate a luminescence. And the luminescence gets modulated by this tag. Now is more simple. Some of the modulated luminescence gets picked up by the reader, which in this case is a passive reader. Passive reader does not actively illuminate the solar cell. So it gets simplified a little bit, but here you have to have some very strong ambient light, like outdoors with a sunny day. Let's talk about some advantages and disadvantages of OFID. Anytime we do communication with light instead of radio, you know, there are advantages and disadvantages. And it really depends on the application that we have in mind, whether we use light or radio waves to transmit information. So let me go through the advantages first. Light, because being light, very short wavelength, it can be collimated using very simple optics, even plastic lenses and plastic mirrors. You can use to collimate or focus light. Right? So you can focus light with very simple objects. to the point that you've probably seen this focusable flashlight. You can focus all that light into a very narrow spot on a wall. Right? All your energy gets concentrated on a small spot. So that's an advantage, right? Doing that with radio requires, beamforming, and you have to work with high frequencies, so your antennas are of acceptable size. It can be done, okay? Collimation with or concentration of radio waves can also be done, but it requires more effort. Another advantage of working with light is that we can use a camera as a receiver. Okay, cameras are sensitive to light, and I just show you in my experiments how using a camera I was able to observe the solar cell. Right? Of course, it has to be a camera that can see the infrared. Right, and therefore you can use a camera as a receiver. And the advantage of using a camera as a receiver is now you can receive multiple transmissions, right? A camera can see multiple solar cells. It can receive multiple transmissions at the same time, okay? But that's not the more, I would say, the main advantage. The main advantage, I would say, is that you can localize. Using a camera, you can localize a transmitter. You can localize a solar cell. You can tell where the solar cell is located. Okay? And that's very important, okay, for some applications that require localization of the transmitter, right? That's a big advantage, all right? Doing that with radio is a lot more difficult, all right? So a radio receiver can receive the transmissions of, let's say, 10 radios, but it's going to be very difficult for this radio receiver to tell where those transmissions are coming from or where are the transmitters located in space. Right? It can be done, but it's more challenging. Here with a camera and of course some DSP, computer vision software, it can be done. Another advantage, I would say, these OFID devices, they don't have to be in front of a reader. They can just use ambient light to power themselves up. Okay, so they can rely on ambient light or ambient energy to power themselves up and do something, even when the reader is not present. OFID tags, because they work with light, they can be placed on metallic surfaces without suffering any detuning. Like that's a challenge for radio transmitters when they are very close to or on a metallic surface. It detunes the antenna, or even worse, it will absorb some of the emitted radio waves. Underwater, and this is especially for seawater, right? Salt water absorbs radio waves a lot, right? So if you put a radio transmitter under the ocean, it's going to go a few inches, and that transmission is going to disappear because salt water absorbs radio waves very strongly. If it's maybe a river or a lake where you don't have a high context of salt, radio can go farther, but it still gets absorbed by water. Light, on the other hand, it can go farther than that underwater. So this could be another advantage, working underwater or inside liquids. Also, I would say OFID, because it uses light, it can work in areas or environments where radio transmissions are discouraged, like hospitals or airplanes, where radio might interfere with sensitive equipment. Okay. Disadvantages: at present, these gallium arsenide solar cells are expensive, much more expensive than silicon solar cells, and so that presents a challenge. But I would say economies of scale can bring it down, right? So if gallium arsenide now find another application, like for communications, now there's a new market So there will be an incentive for companies to fabricate gallium arsenide solar cells in large quantities, and therefore their prices can come down. It requires line of sight, and this is true for any optical communication, right? If you put your hand, you can block the light. You close the door, you block the light. All right, so this could be an advantage, and also, for secure communications, where if I close the door and I don't want anybody to, to receive my transmissions, that's very easy to do with light. You just close your door and nobody sees your light. But for radio, you close your door and the radio waves still come out of your room. So a line of sight could be an advantage and a disadvantage, depending how you look at it. Also, I would say line of sight is not a total killer. I show you in the experiments how infrared light was able to reflect off of the table and off of the walls. Right? So it will be possible in some situations to catch, reflections, at least one reflection of some object. Because solar cells they have a large size. They are made on purpose to have, large areas so they can capture more light. They also have high capacitance and internal capacitance, and that's going to limit the speeds that they can work. So we're talking about a few tens of kilobits per second. Okay, so we're not talking about megabits, Wi-Fi type of speeds. Imaging receivers. I was talking to you about cameras, how cameras can be used as a receiver. And that's great because they can localize transmitters, but cameras also are limited by the frame rate. Right? Normally, a camera will have a 30 of 60 frames per second, and that will be, the maximum speed you could receive information. You could go higher, cameras with 1,000 frames per second, but they're more expensive. It can be dirt, it can get dirt on top of the solar cell can, dust can accumulate. So that's another challenge, right? You have to, if it's outside, will have to be clean, or otherwise, if that's accumulate over the solar cell, you're going to lose some of its luminescence. And if you're collimating light, meaning you're putting most of your energy in one spot, then you have to point it, right? If you have a flashlight, and then you focus the flashlight on a particular spot, that means that you have to, if you want to illuminate a different spot, you have to move your flashlight. That means pointing, right? So collimation is great because it focuses all the energy into one spot, but then you require pointing. Anyway, so let me talk about applications, potential applications of OFID. Let's try to imagine for a moment that the solar cells are available, and we can come up with the circuits to do all the things that I showed you before. Right? If we can turn them on and off at will, and we can come up with a nice devices that are nice and thin and small. Then perhaps you can put them at home, indoors, on a wall, and the solar cell is going to be receiving energy from lights, from indoor lights. It's going to be charging, if you will, from the lights. But also these LED lights, they can blink and transmit information to these tags, and these tags, using luminescence, can reply back, by blinking their infrared luminescence. So they have a wireless device for smart homes, for instance, where you just put it there, you forget about it. They don't require you to change batteries because they receive energy from the lights, and they have optical bidirectional communication between the lights and these devices. We could also imagine a factory floor or a warehouse where you have boxes or robots moving around. And let's imagine if for a moment that we put, these tags on boxes, right? So, and these tags, maybe you can put some sensors to detect if the box has been dropped or not, all right? So you can have more lights in your factory floor, and some of these lights also can blink and can transmit data to the tags, asking to transmit back. And so these tags could transmit back using the luminescence and transmit their sensor readings. And by doing that, they also can be located, right? So that's, I would say, a big advantage on a warehouse if you can locate your boxes, right? By detecting where the blinking is coming from. Outdoors, this is more like perhaps for scientific applications where we want to monitor some environmental variables, maybe soil properties, or properties of the air, and we deploy these sensors that have a solar cell, and the solar cell is being used to capture energy and charge the sensors batteries, but it can also be used to transmit information back to a drone, for instance, in this case. Other applications, here I skipped the indication of this fish or some food or some perishable items, could be food, could be medicines, where you place a tag and this tag is measuring the temperature as this item goes through the supply chain. It's only relying on ambient light to keep itself powered and do measurement of temperature. And when this device or this item goes under a reader, then the data can be read out. Here I was showing you the case of a baby, right, in a hospital, right? We want to measure temperature of this baby in an incubator. You can put a radio, but some parents might be hesitant to put a big radio transmitter, not a big radio transmitter, but a strong radio transmitter right on the baby's body. But if you do it with light, there's less concern, right? I mean, if you do with RFID, you will have to put a RFID antenna under the baby and radiating the baby as well. But if you do it with light, the concern is minimal. In this other situation here, I'm showing like containers, metallic containers, and again, placing a radio transmitter on a metallic container is a challenge because of the deep tuning. Or the interaction there's going to be between the antenna and the metal. But if you use light, collimated light in this case, you can read, you can point to the tags and you can read that information without having to worry about deep tuning. This is out of the world kind of application for satellites. Satellites also use these very efficient solar cells that exhibit the luminescence. So in this case, CubeSats, you can point to them and ask them to blink, and they can blink saying, hey, I'm, satellite number 1 or satellite number 2. This could be applicable for, CubeSat, where you release a lot of CubeSats, tens or hundreds maybe of CubeSats, and then you want to know which one is which one. Right. So these CubeSats, using their solar cells to transmit a message or a code saying CubeSat number 1 and so forth. Maybe also for animal tracking, right? So this is, for instance, showing you here, what if you want to track bees, right? So you want to see which flowers do they prefer to go, or where do they go when they leave the hive, right? So there's been this group in Australia that has placed RFID tags, very small RFID tags on bees, and using that, you can detect when a bee has left the hive and when it has returned, right? Because it also put an RFID antenna at the entrance of the hive. But what about when the bee is flying around, and it's not under the influence, or it's not too close to an RFID reader, then you lost contact with that RFID reader. So, but if you use an RFID tag, and you could follow this bee as it goes. It's today because you can make this the solar cell. It has to be a tiny solar cell. Also blink, and we can follow this bee. This is an extreme case, right? It has to be very small solar, very small circuits. We're also thinking of bigger scale for chickens or ducks. Chickens in a coop. Right, we're talking about very large systems where you have hundreds of, if not thousands, of chickens under the same roof, right? And then you want to do, for instance, you want to follow the chickens, see if they have eaten or not, and you want to also be able to tell where have they been inside the housings. What kind of interaction they have with other chickens, perhaps in the context of a virus or spreading through the chicken, right? You can do contact tracing if you are able to follow the animals inside the housing. All right, so maybe one more potential application for smart cities. You could have also maybe a car or buses and the cameras that are already there to monitor traffic could be used to also pick up these transmissions. All right, so that's, yes, the first part of my presentation that kind of gave you the big concept, perhaps motivate the work with some applications. So what I want to show you now is a more technical detail about how we go about building the circuits that we need to build to make these RFID possible, right? So I'm going to show you a little more technical detail from the circuits perspective also. And so this is the second part of the presentation. So what I'm showing you here is a solar cell. Okay, we use a diode symbol because really it's a diode. It behaves like a diode. And this is what we call an IV curve, a current versus voltage curve of a solar cell. Excuse me. It looks like this. So if I measure the current, in this case, the current going into the solar cell as I change the voltage VD of the solar cell, and if I plot that, I will get a curve that looks like this. Exponential curve. This is a curve of a diode. So if the solar cell is dark, there is no light falling into the solar cell, you get this type of response. But if you illuminate a solar cell, you also get an exponential response, but it has moved, it has shifted now, shifted down. Now you have this type of curve. Okay, it went down by this amount, IPH. IPH, we call that the photo current, right? And so this is voltage, right? When voltage is negative across the solar cell, you see the current being constant. And then as soon as the voltage becomes positive, the current starts to decrease, less negative, until it becomes zero, and then becomes positive. Okay, and it rises very fast. After that is an exponential increase. All right, so what we have here is these three different regions. In this region, when the voltage across the solar cell is negative, we call that the reverse bias region. Okay, voltage is negative and the current is almost constant. Right? Once the voltage becomes positive, the current starts to decrease very rapidly. Okay, We call this region the photovoltaic region. Okay, voltage is positive and the current is negative, but it's negative going into the solar cell, meaning it's coming out. Okay, it's positive, it comes out of the solar cell. And when the VD keeps increasing, now VD is positive and the current also is positive in this direction, right? We call it a forward bias region. All right, so we have now 3 different regions. So this region is very important for energy harvesting. This is where the solar cell generates power, right? Look at this, the voltage is positive, the current is negative, but negative in this direction, meaning it's coming out of the solar cell, it's going in this direction. So you have something that gives you positive voltage and a current output. That's behaving like a battery, right? It's generating power. But in the reverse bias region, the voltage is negative, okay? The current is still negative, so the current is coming out, but the voltage is negative, right? So in that case, the solar cell is consuming power, dissipating power. It's not generating power, it's consuming power. And the same is true if you look at the forward bias region, right? So in this case, voltage is positive, and the current is positive in this direction, meaning it's going into the solar cell. And therefore, the solar cell is also consuming power. So the solar cell only generates power in this region, in the photovoltaic region. Okay, so this is where we want to operate if we want to harvest energy from the solar cell. At one point along the region, there is this point called the MPP, the maximum power point. This is where you are going to be able to draw the maximum power of the solar cell. If you work at this point, you're going to draw 0 power because you have 0 current. You know, you have some voltage, but 0 current. The power is 0. The other point here is here you have a lot of current, but the voltage is 0. Here you have 0 power as well. Something in between these 2 points of 0 power, you will have a maximum power. MPP. Okay, so that's the basics of solar cells. And so what we're going to do here, another experiment, very, very simple experiment, where we're going to have a flashlight. The red flashlight is going to illuminate the solar cell. Okay, and I'm going to change the voltage of the solar cell. I want to change, I want to do this kind of IV measurement where I'm going to change the voltage across the solar cell. Instead of measuring the current, I'm going to measure how much optical power I can detect with this optical power sensor. Okay. And so I'm going to have a curve that looks like this. Okay, here the x-axis is voltage. Like in this case, I'm changing the voltage across the solar cell, but I'm measuring the optical power with this power meter. All right. And what do I get is an exponential response. Just like I did for current, I get an exponential response for the optical power. Okay, so it's very low at first when the voltage is low. When the voltage gets to a point, crosses about 1 volt, it starts to increase very fast. Yeah. So a few points of interest here are the maximum power point, the MPP is here. We have the open circuit, that will be this point here. And we have also the short circuit, that will be this point here. So 3 points of interest, SC, MPP, and OC. Okay. So by the way, for instance, this curve already suggests how we could modulate luminescence. For instance, we can go from open circuit to short circuit, right? That can modulate luminescence. That will be the experiment where I was doing with my hands, going from open circuit to short circuit. But we can also go from open circuit to MPP. Open circuit to MPP. That's another way, another possibility for modulation. So phi lambda is this flux, the radiant flux that comes out of the solar cell. We call it phi lambda. So here a bit more modeling to go deeper into the circuits. Usually a solar cell, we model a solar cell with a diode, a current, some resistance and capacitance. In this case, because we're trying to modulate, to model the luminescence, we're going to model it with an LED. Right? So this diode is also going to be an LED, and it's going to be emitting light. This is phi lam, representing the light in the radiant flux. All right, so this is our model. So we say that this light that comes out of the solar cell has two components. One is due to the light coming in. This phi in is the flux, radiant flux coming in, and phi lam, the light coming out. So there is one component due to phi in, that will be the photoluminescence component. And there is also a component due to this current flowing into the diode. So that will be, if you will, the electroluminescence part. So once we have these equations, here's what all these arrows mean, we can start doing some modeling, right? So we can start analyzing some circuits, okay, and looking at their performance. All right, so here we're gonna see how we can modulate the luminescence, see if we can come up with a circuit. Those three things that we wanted to do, right? We wanted to modulate luminescence, we wanted to harvest energy, and we also wanted to receive information. All right, so let's assume we have a circuit here that's called, we're going to do the modulation and also energy harvesting, okay, in between the solar cell and the load. All right, I want to know what can we put here that we're able to modulate and harvest energy at the same time. Okay, so let's consider a very simple modulator, a resistor. Let's say I place here a resistor, a variable resistor, and connected to the solar cell. And the solar cell has phi in, the light coming in, phi lam, the light coming out. Okay, current coming out of the solar cell, voltage across the solar cell. And let's put this resistor are equivalent. All right. It turns out that this is a very simple circuit. We can write down the equation for this circuit. Okay. It's very simple. What complicates the circuit is that this diode is nonlinear. Okay, so we have this nonlinearity, this exponential here. Okay, that complicates the analysis a little bit, but it's not too bad because it's very simple. All right, so we can solve for this circuit, and we can solve for the voltage across the solar cell as we change the resistance. Right, so here's the resistance Req, and this is the voltage across the solar cell. So we can see as we change the resistance, the voltage is going to change, okay? But it's going to change, and it's going to reach a point where it won't change anymore, okay? Why is that? That happens when the resistance is very large. We're here at 1 mega ohm. That's equivalent to an open circuit, right? So when you reach the open circuit type of situation, the voltage doesn't change anymore. That will be the open circuit voltage of the solar cell, right? At one point, here's the maximum power point. And if you go too short, too small, if Req is too small, it's like placing a short here, and you will be at a short circuit here. All right, so here, at this point where we reach the MPP, at this point we call the resistance the RMPP. Okay, so here's the resistance will be equal to resistance that biases the solar cell at the MPP. We call that RMPP, and this is the open circuit voltage. Okay, so let me show you a practical circuit, something that we can use to accomplish these two things, modulation of luminescence and energy harvesting. It's all based on this very common and well-known circuit, that boost DC-DC converter. Okay, so this circuit uses an inductor, a transistor, and some capacitors to draw energy from the solar cell and pass that to a load. Okay, in this case, a resistive load. So think of this inductor as a bucket. Okay, but instead of being a bucket for water, it's going to be a bucket for charges. Okay, so when this transistor closes, it's closed, it's going to connect this inductor to ground, this end to ground, and you're going to have the inductor connected to the solar cell and then to ground. That's going to charge the inductor. Okay? It's going to charge our packet. Okay, and then we're going to open this transistor, and all this charge that was in the inductor wants to go somewhere, and the only way it can go is through this diode and into the load. And that's when the packet charges. Okay, if we do that very fast, open and close this switch, we're gonna use this inductor to move charges from the solar cell to the load, and in the process, that voltage is gonna be stepped up. It's gonna be boosted. Okay, so this voltage here at the load is going to be larger than this voltage here at the solar cell. So if you started with, say, 0.8 volts, you might end up with 6 volts, 5 volts. Yeah, right? So it's moving charges from the solar cell to the load, and in the process, it's boosting the voltage, okay, by using this inductor and this switch. All right, so it turns out that this frequency at which you're going to close and open this switch is very important. Okay, not only the frequency, but also the duty cycle of this signal that drives the gate of this transistor. It has to be just right. Okay, if it's not right, you won't get a good voltage here. Okay, so that's just the DC converter. That is a well-known circuit. So we're going to modify it. We're going to modify it, and we're going to give it an input. We're going to call it V mod. Okay, and this input is going to be controlled by the bits that we want to transmit. In this case, I have 4 symbols: 1, 1, 1, 0, 0, 1, 0, 0. Okay, and the data that I want to transmit is going to control which voltage do I apply to this modulator. And what this does is changing the pulse width of this clock based on which bit I want to transmit, which pair of bits I want to transmit. That's the basic idea. Well, it turns out that this circuit we can also analyze, all right? And we can look at the input impedance of this circuit Rin as a function of the duty cycle. Okay, so this rho is now the duty cycle of this clock signal here. Okay, the input impedance changes as a function of the duty cycle. Look at this. Right? Because it's very high at first when the duty cycle is too small, and then goes down. Okay. And so what this tells us is now we have a way of changing the impedance, right, of this boost converter. It's changing its impedance as you change the duty cycle. Okay, which is exactly what we needed from the previous slide. I show you that if you change the resistance that you apply to a solar cell, you are going to change the photoluminescence. Now we have a practical circuit that does that. By changing the duty cycle, I change the input impedance. By changing the input impedance, I change the voltage across the solar cell, and I change the luminescence. Okay, so we can put all these things together, and then we can have a relationship between the duty cycle and the luminescence. Okay? It's going to look like this. Okay, it's not linear, right? You can see it's going to go down. Luminescence is going to go down with duty cycle. And it's going to reach a point where it's not going to change anymore. Okay. And so again here, I can highlight all these 3 points again. The open circuit. When this duty cycle is so low that it never turns on this transistor, that's the open circuit. Or it's so high when this transistor is always on and it's always doing a short circuit to the solar cell. And in between, you're going to have the MPP, the maximum power point. All right. So here is the connection, right? And that's what this circuit is going to exploit, this relationship between the luminescence and the duty cycle. Here I'm showing you this voltage, V out, how it's going to change with duty cycle. Right? For some duty cycle, it's going to be maximum. okay? And then if you keep increasing duty cycle, then it falls. Right? If the duty cycle is too short, then the voltage is not maximum. But at one point, in this case, about 20-something%, the voltage is maximum. And that's an MPP, right? When you maximize the output of the load, that's when you have a maximum power transfer. Right. So when you look at this from the point of view of energy harvesting, of course you want to operate here, where you have maximum power transfer from the solar cell to the load. So you want your duty cycle to be exactly that. Okay. But if you want to transmit data, right, what this circuit is telling you is you want to move your duty cycle away from the maximum power point, right? So here's your duty cycle for the maximum power point. If you want to modulate luminescence, you are going to have to move away from the maximum power point so that your luminescence changes. Okay? So you're going to have to give up a little bit of energy, harvested energy, all right, to be able to change the luminescence, move it away from the maximum power point. Okay? So that's a trade-off that we have in this circuit in particular. But if we want to use the solar cell to transmit data back using the luminescence modulation, then we'll have to give up some energy, all right? Some energy that we won't be able to harvest because we have to move away from the maximum power point to do that. And that's a trade-off we have to accept. In any case, I told you that we like circuits, and so we built this whole system. Right, here's our modulator I showed you before, and here actual part numbers and actual value of components that we used. Right, so we have this little oscillator that you can change. It has an input called mod, and you can change the duty cycle of this oscillator. You can connect this to a waveform generator, and we can change this voltage V mod. By changing this voltage V mod, we're going to change the duty cycle of this clock, and by changing the duty cycle, we're going to change the luminescence, by the results I showed you before. Here's the solar cell, and we have an LED here with some lenses illuminating the solar cell, as you can see here. And here we have another flashlight. We modified, we removed the LED and we put a photodiode instead. Okay, it's going to be a receiver. And then we have some amplification, some filtering, and the oscilloscope. And the oscilloscope can capture all these waveforms. And so these are the waveforms that we capture. Here's V mod. So V mod, this input here, goes linearly from 0 to about 1 volt. Okay, so it's going to be changing the duty cycle. As the duty cycle changes, you can see this voltage VPL, okay, which is the amplified version of this current that is picking up. Look, it's going is going up and then down, right? Up and then down. Just like our previous slide predicted, it has the same shape, open circuit and then goes down, maximum point. And so this is nice to see, it matches the theory. But if you zoom in, you see all these things moving up and down. That's a switching noise, okay? And that's due to this switch going up and down, up and down, up and down. That creates all different noise. But we can filter that out. Okay, we can remove that noise. Here's V out, right? If you look at the output here across the load, you can see that it goes up. It's maximum at the power point, right, which is over here, and then it goes down. Okay, so that was just a linear increase. We can put some steps instead of just linear increase. We can put some steps, and you can see what happens here at the output of this receiver. You also see those steps. Okay, embedded, you can see that noise, the switching noise there, due to the action of this transistor. Again, that's high frequency noise. We can remove it with a low pass filter. Okay. You can see what happens to the voltage at the output here. Here, the voltage at the load is about 5 and something volts. It's not as maximum. It's not as high as the MPP. voltage, right? And again, this emphasizes or highlights this trade-off, right? So we were able to modulate the luminescence, but at the cost of giving up some harvested energy. This is where we filter out the ripple noise. This is the switching noise. You will get nice signal. All right, so I'm going to show you some circuits that maybe a simplified version of what I showed you before. So instead of changing the duty cycle of the clock that drives this MOSFET, I'm going to put another MOSFET in between. Okay, and then I'm going to feed the data here. And what this MOSFET is going to do is going to do an open and short, right? So when this MOSFET is open, then the solar cell is open circuit. When this MOSFET is closed, it will be connected to the DC-DC converter, and it's going to be at an MPP. All right, so this circuit is going to do a modulation from open circuit to MPP, open MPP, open MPP. And this circuit is going to do something a bit different. Look at this. We're going to keep our clock to a fixed duty cycle. We're going to put an AND gate, and we're going to AND the clock and the data. Okay. So when the data is 0, the output is 0. Okay. And this transistor is off. When this transistor is off, the solar cell is going to be an open circuit. When the data is 0 or 1 rather, then this clock goes through, and now this DC converter works as normal, and we're going to be able also to modulate the luminescence. Okay, so again, this is going to go from open circuit to MPP, open circuit to MPP. Different approaches. Okay, so here AND gate, here is a transistor in front. Again, I told you we like circuits and we like to implement circuits. So this is an implementation of that and showing you the power and the bit rate. Now I'm just looking at my phone. The time is it's already 10:19. Okay, so time has flown by really fast. I didn't realize we are over, an hour. So I don't know how many of you are still listening. I have a few more slides. We can either go through those slides very quickly, or we can stop here for questions. Is there any preference?
Yes, Shri, can you?
Yes, sir. Yes, sir. Here a few questions are there from participants. So I'll just read one. One question is from Silicon 14 Lab. So they have asked how OFID solar cell is different.
Efficient at emitting light. We can also use LEDs. All right, so that's on the slide I have at the end. LEDs are also they can work as solar cells. Okay, they're not the best solar cells. Okay, but they can also work as solar cells. So you could use an LED as well. You said there was another question?
Yes, sir. We have another question from Kamal. He has asked, how long in near future you feel that this technology will be used for communication?
Good question. Well, I hope it's very soon, right? Next, we're already building our prototypes. You can see in the screen now an actual prototype. This is our first prototype. We're thinking about developing our own microchip. So it's hard to tell because it really needs to, many things have to happen, have to fall in place, right? Like the demand, we need to find a good market for this, right? And again, somebody who manufactures the solar cells that we need. So if all these places all these things are in place, we can say in 2 years, I don't know, 3 to 5 years, we could have a product. It has to be the demand, right? It has to be a market. because we can have the most amazing circuits or devices. If nobody wants to pay for them, there's not a market. So it's important because there should be people or companies willing to pay for this, customers. And that comes down to the applications. It has to be a good application where where radio is just not the best solution. But light is the best solution. To answer your question, I hope if, within 3 to 5 years.
Few more questions, sir. There is one more question from Arul Mudamil. He has asked, will the technology be used to save a child or rescue a child accidentally if he is fallen in a borewell?
The child that has been that fell into a what?
Borewell.
Ah, good question. I don't know. That you caught me by surprise. So if a child is wearing one of these beacons or these tags, maybe I would say maybe, but so if the child has fallen into a borewell, you probably want a radio transmitter there, so the radio signal comes out of the borewell and can be detected by somebody else. Right? In the case of light, if you use light in that case, I'm thinking out loud right now. If you use light in that case, you might it might help you locate the child when you look into the borewell, but it might not alert you when when the child fell into the borewell. So it might be helpful if you already knew it fell, and then you want to locate where he is inside the borewell, but maybe not to detect the fall in the first place. But good application, good question.
So we have one more very important, interesting question from Paul. He has asked that is there any possibility of online internship during this COVID situation, because we cannot travel now for a year. So is there any possibility for online internship?
Good questions. Wow, you guys are full of good questions. I haven't thought about that, and that's true. There is no. I think it's possible. I'm open to the possibility. The challenge is that, like you saw, we do a lot of hands-on. We like to do circuits. We like to do experiments. So that part won't be possible remotely. But certainly, what could be possible is simulations or signal processing. For instance, I mentioned that we want to use cameras as our receivers. So that is signal processing and computer vision that can be done remotely. Right? That can be done, at a distance. We will probably have to capture data here and send you the data, and then the student does the processing in Chennai. So maybe from that perspective, it is possible simulations or maybe processing data that has been captured here, and then we make it available to you guys, and you can do some MATLAB processing. Yeah, I'm certainly open to that possibility.
One more question, sir, from participant Sudha MR. She's asking, can you please explain how solar cells are used in data center for generating power?
In data centers, I haven't seen, well, you mean outside the data center or inside the data center? I suppose outside the data center. On the roof of the data center. I think that's what she means. So for a data center would be just like a regular a solar cell. In that case, the solar cell is just, or a panel, right? Many solar cells together to generate power. So in that case, it's just used to convert sunlight into electricity, right? There is no modulation of luminescence and so forth. So it's just the regular, typical application of a solar cell as energy harvester. Now, for a moment, I thought she was asking about inside inside a data center, to enable communication between servers, maybe. I don't know, maybe not practical, very practical, because like I said, solar cells are good for low rates, low speeds. In the data center, I would expect the communication to be at very fast rates, megabits per second, gigabits per second even, right? So good question, but I think for a data center, the solar cells will be, the traditional application of solar cell. Convert sunlight into electricity.
Okay, similar, we have one more question from our staff member, Ambika. I think the answer is same for what you have answered, sir. Similar only. Here she has asked, how can you elaborate how energy harvesting happening in antennas during night time? So I think the answer is same only.
Okay.
Like data center, what you have explained. So since we are running short of time, we will answer all the questions. We'll get the answer from the for the questions from sir, and we will post to the participants through their email. So we are concluding this session now. Now I request our beloved HOD madam to give vote of thanks.
Professor, are you done with the presentation, or you would like to conclude the session? And then I will go continue.
I have a few more slides, but I realize it's Friday night. For you guys, I don't want to keep you. What I can do is really quick, browse through these things, because at this point, I don't have too much theory, but I just have some prototypes. That's what I could do, maybe show you some of the prototypes. We've done more experiments. Here is, we try to make things very small. We use FPGAs, that kind of, again, we like circuits and we like to miniaturize them. And things like that. I was going to highlight also the work done by Sindhu. Sindhu, as a student from Crescent, she was here for a year last year, and she did all this work that resulted in on a paper that's right now in the review. And so I wanted to highlight her work as well, and that's what she worked on. Maybe at the end, leave you with some, future directions. Like I said, LEDs are also interesting because LEDs can also work as solar cells, and of course they can emit light very well. So we're also interested in pursuing that direction, especially for underwater communications. And then maybe highlight some possible directions for future. There are these tandem solar cells where you have silicon on the bottom and then something else on top, like perovskite. So that could open also some possibilities. And then that's it. Then at this point, thank all the students from Crescent here, our sponsor, and thank you very much for your time.
Thank you, Professor. That was a wonderful presentation by you. And really, it was interesting and inspiring for us, and hope for the participants too. We have received a lot of positive feedbacks from many participants, and we will be sharing it to you. And at this juncture, I would like to thank all the participants. We had more than 500 registrations for this online webinar, And thanks so much for all the participants out there. And thank you so much, Dr. Leon-Salas, for your time. And also, I would like to thank Dr. Vijayalakshmi, Dr. Parnashri, Mr. Inyaman, and all my entire department for making this webinar possible. Thank you, one and all. Doctor Sir, have a good day, and thanks for your time. Dr. Leon Sir.
Thank you. Thank you very much. Thank you for your time. Thank you for your questions. Have a good evening.
Thank you, sir.
But a man is poor without dream and ambition. Learn, innovate, and empower.
The Electronics and Communication Department of B.S. Abdul Rahman Crescent Institute of Science and Technology is established in the year 1994, celebrating its 25 years of excellence, accredited by NBA, aspires to be a leader in education, training, and research in multidisciplinary areas of importance and to play a vital role in the socio-economic progress of the country.
The institution is renowned for its technical competence, intellectual character, commitment to excellence, community focus. What creates an indispensable future? Charging the neurons to waver the world
with the brains as a transmitter, enchanting the engineer look.
Electronics and Communication Department is known for its excellent lab facilities, 14 in number, with highly motivated faculty. In the focus to develop the interest of the students, the department has inaugurated clubs like Hobby Electronics